All right, we are in section 3.9, which technically is a part of the last chapter, even though this is really kind of what builds into the new chapter. The last chapter had to do with derivatives, so the fact that we're calling this an antiderivative, I guess still technically fits with the last chapter, but this really is going to play a part more in what we're going towards for chapter 4. So an antiderivative is exactly what it says. It is the anti, or the opposite, of a derivative. So let's talk about what that is and how to calculate an antiderivative. Really, this is probably one of the easier lessons that we do all year, so you probably will like this one. So the first thing is find f whose derivative is lowercase f of x equals x squared. Or in other words, what would the function have to have been for me to get x squared as a derivative? And you might have to think about that one for a little bit. So to get x squared as a derivative, I think I'm going to need to have had a, oops, moving the paper all around here. I think I'm going to need to have had a 1/3 x cubed. Because if you take the derivative of 1/3 x cubed, you would bring the 3 out to the front, multiply it by the 1/3, you get 1, and then reduce the power by 1, you'd get x squared. So you'd get 1/3 x cubed. So here's the big thing. Note that capital F of x is an antiderivative of lowercase f, not the antiderivative. And that's because of this. Let's say that I started off with capital F of x being 1/3 x cubed plus 7. If you take the derivative of 1/3 x cubed plus 7, don't you still get x squared? Maybe capital F of x was 1/3 x cubed minus 200. If you take the derivative of that one, don't you still get x squared? So 1/3 x cubed was an antiderivative of x squared. It's not the antiderivative of x squared. And that's because we can technically have any of those numbers attached to the end of this thing, added or subtracted, of course, and the derivative is the same. So here's the theorem. And this is not a theorem you actually have to memorize by name or anything like that. You're going to know how to use it pretty much. If f is an antiderivative of lowercase f on an open interval, then the most general antiderivative of f on I is capital F of x. So when we take an antiderivative of a lowercase function, we usually use the capital letter, plus some constant, and we call that c, where c is just an arbitrary constant. So the general antiderivative is a family of functions. Okay, what does that mean? Let's take a look graphically. If we were to take an antiderivative of 2x, f of x equals 2x. So capital F of x. Now think, what would I have to have had to get the derivative of 2x? Well, I would have had an x squared, right? Because x squared's derivative is 2x. So I would say x squared, but I have to add a constant c. Well, let's fill in values for c, and then we'll see what we mean by this family of functions. So let's just say the easy one, c is 0. So then f of x would simply be x squared. That's your basic parabola. Looks like this in general. Okay, and that's if f of x is x squared. Let's say, for example, f of x is x squared plus 2. Okay, now we're going to let c equal 2. All that means is I've taken x squared, and if you remember your shifting, that shifted the entire function up 2 units. So basically, it would look something like this. That would be f of x plus 2. And maybe instead we want to do f of x is x squared minus 4. So now c is negative 4. All that does is shift the entire thing down 4 units. So now it looks something like this. So hopefully what you can imagine here is that I could let c be any value that I want to, any constant. And it literally will be every single parabola that you could draw in the shape of x squared that is slid up and down the y-axis. Okay, again, I'm hoping that you can kind of see that. That means that there is no space technically in between every one of those parabolas. It is a family of functions of x squared. It's every possible x squared that could be drawn up and down the y-axis. Now, there's obviously space in between the ones that I drew because I picked values that you could easily see. But you could have c be 2.00000000001, and it's basically going to look like it's almost exactly the same place as the green one. It'll just be slightly higher. Okay, so that's the concept of an antiderivative. We are literally taking the derivative or something that we have and going backwards. We're trying to figure out what we would have had to take a derivative of to get where the lowercase function was. Okay, it's not as hard as what I probably just made it sound right there. So, if I were to tell you, and this unfortunately is where being able to do this in class is awesome, because I love to be able to actually work with people and see them figure this stuff out. But since we're doing it through a video here, I don't have that option. So if we were going to take the antiderivative of 4 plus x squared minus 5x cubed, you might have to do a little bit of thinking here. So what would the antiderivative have to be to get 4 as a derivative? Well, you'd have to have a 4x. We've already done the x squared. We did that on the other side, and we said that was 1/3 x cubed. Now it's going to get a little tougher. The antiderivative of 5x cubed is going to be 5/4 x to the 4th. And then don't forget, because it's a general antiderivative, we always have to include a constant of integration, or no, it's not constant of integration, just a constant plus c. So now you might ask yourself, how did you figure this one out so fast? Well, think about it. This is exactly the opposite process of a derivative. A derivative said we would bring the exponent out to the front and then reduce the exponent by 1. Well, we're going to do exactly the opposite. Instead of bringing the exponent out to the front and reducing it by 1, we're going to go backwards. We're going to add 1 to the exponent, and then we're going to divide, instead of multiplying, the coefficient by the new exponent. So, in general, your f of x, or your antiderivative, is going to be taking the function and adding 1 to your exponent, and then dividing by that new exponent. And don't forget your plus c. So now let's see if we can work it out with the next one. Again, this is really not that difficult to do. So in this case, our antiderivative is going to be capital F of x equals, if I add 1 to the exponent, and then I divide by the new exponent, which is 21, I could write it like this, and that's perfectly acceptable. Personally, I prefer not to do it this way. Dividing by a number is the same thing as multiplying by its reciprocal. So I prefer to write it out in the front as the reciprocal. So dividing by 21 is the same thing as multiplying by 1/21. Okay, those mean the same thing. All right. So in the next one, add 1 to the exponent. We now get to the 11th. We'll divide the 4 by 11, and we get 4/11. Now in that one, it was okay just to divide because we already had the coefficient out there. Technically, what we did in the first one was we divided the 1 coefficient by 21 as well. It's the same thing. And then the last one, since it's a constant, the antiderivative is always going to be that constant times x. And don't forget plus c. Okay, couple more examples. Capital F of x here is going to be, let's see, the exponent on the 2x currently is 1, so we'll raise that by 1 and get x squared. Dividing the 2 out in front by the 2 that we just got for the exponent makes it 1. And that should make sense. The derivative of x squared is 2x. Now, it's got a little bit different one here because we have a decimal exponent, but it's the same idea. We're going to raise the exponent by 1, which is going to be to the 2.7, and then we're going to divide the coefficient 3 by 2.7, and don't forget, plus c. Let's actually make that look like a 2.7. Now, this is an acceptable answer. It's just not the way you would probably see it because we don't typically leave decimals or fractions on top of other decimals or fractions. So the easiest way to do this one is to multiply the numerator and the denominator by 10. That's just going to move our decimal places one space to the right. And then hopefully you can now see 30 over 27 will reduce because 3 goes into both of them. So this is going to be x squared plus 10 ninths x to the 2.7 plus c. And there's your general antiderivative. Okay, number 4, you need to change these things into a power so that you can basically use, this is the power rule for antiderivatives. So we're going to change these. So the 4th root of x cubed can be rewritten as x to the 3/4 power. And the cube root of x to the 5th can be written as x to the 5/3 power. Now I can take an antiderivative using power rule. So you are going to have to be good at adding and subtracting, again, 1 from fractions pretty quickly, I would say. So the capital F, or the antiderivative of our function, let's raise 3/4 by 1. That's going to be adding 4/4, so we get 7/4. And then divide by the new exponent. Now dividing by 7/4 is the same thing as multiplying by its reciprocal. So we're going to multiply by 4/7. Plus, let's raise 5/3 by 1. So we're going to add 3/3, so we get 8/3. And then dividing by 8/3 is the same thing as multiplying by 3/8 plus c. There are your general antiderivatives. All right, let's move on. More examples. Now, g of x is a little bit different because it's a quotient. And while there are going to be some future rules that we can use to do quotients, in this case, we actually can't. We're not going to be able to use anything here to do this simply. So what we have to do is do a little algebra up front. We're going to divide every term by x to the 6th. So 5 divided by x to the 6th is just 5 over x to the 6th. But I want to write it in such a fashion that I can do this kind of linearly, so it's going to be straight across. So instead of writing 5 over x to the 6th, I'm going to write it as 5x to the -6. That way we can use our power rule. Okay, we're going to do the same thing on the next one. So 4x cubed over x to the 6th is going to reduce to 4 over x cubed, so we're going to have 4x to the -3 power. And then the last one's probably the easiest because it's 2x to the 6th over x to the 6th. The x to the 6th will completely cancel out and you'll just get 2. Okay, that's just rewriting it to make it easier to take the antiderivative. So now the antiderivative, capital G of x here. Now, this is, be careful, add 1 to your exponent. So the first one, -6 adding 1 is going to give us to the -5 now. And then dividing the coefficient 5 by the new exponent -5 gives us a -1. So we're going to get a negative out front. And if you haven't already been able to tell, this is why I haven't been writing the coefficients first. So the next one, x to the -3, if I add 1, I am at x to the -2. But dividing the coefficient -4 by -2 actually gives us a +2. Again, that's why I have not been writing the signs and stuff in the coefficients. And then the last one is a constant, so the antiderivative is just 2x, and don't forget plus c. And you could certainly rewrite those without negative exponents if you want or need to for something in the future, but for now, that's the general antiderivative. You're fine. Okay, number 6. Number 6, you just have to know your trig stuff. So if I'm going to take the antiderivative of lowercase f, ask myself, what would I have to have had to get a derivative of 3 cosine t? Well, my original function would have had to have been 3 sine t. Take the derivative of that, you get the 3 cosine t. What would I have had to have gotten negative 4 sine t? Well, the derivative of cosine is negative sine, so this is going to be plus 4 cosine t. And I wish I could tell you there was some power rule trick for this. There isn't. You just have to know all of your trig derivatives so that you can go backwards. And then again, don't forget plus c. Okay, and the fact that the variable changed to a t doesn't matter. It's the same process, just like it is in number 7. The fact that the variable here is a theta doesn't change anything. It's just another variable. So we treat it as such. So 6 theta cubed will add 1 to the exponent. I'm sorry, 6 theta squared. We add 1 to the exponent and get theta cubed, and then divide the 6 by the new exponent 3, and we get 2. And now the secant squared part, again, you just have to know that the derivative of tangent gives you secant squared, so the antiderivative of secant squared is going to be tangent. So it'll be minus 7 tangent of theta, and then plus c. So again, with the trig, you just have to know your trig derivatives so you can work those backwards. There's really no trick to those. And then the last one, number 8. So capital F of x, our antiderivative, add 1 to x to the 2/3, and we're going to get x to the 5/3. Dividing by 5/3 is the same thing as multiplying by 3/5. And then x to the negative 1/3. If I add 1 to that, I'm going to be adding 3/3, so that's going to give me positive 2/3. Dividing by 2/3 is multiplying by 3/2. If I take 2 and I multiply it by 3/2, we end up with 3. And then plus c. So again, just be careful when you're adding and subtracting, especially when you end up with the negative exponents. That can definitely be a part where you just make a silly mistake. Okay, we're going to come back with a second video, and we will be done. And since